We're going to do a problem on conservation of energy. This is from chapter 10, number 36. The problem says a fireman of mass 80 kilograms slides down a pole in the fire station. So here's the pole, here's the floor, here's the fireman. So he slides down the pole, and the distance that he travels is 4.2 meters. And when he reaches the bottom, his velocity is 2.2 meters per second. And the question is, how much thermal energy is created? So we're going to use the principle of conservation of energy, which says that the total change in energy is equal to 0. There are no outside forces. The pole is part of the system, so it's internal, doing some dissipative force of friction on the firefighter. So the kinds of energy that we have are kinetic energy, energy of motion, gravitational potential energy, because he's sliding downhill, sliding down the pole, and thermal energy. So all those different kinds of energy change add up to 0. The delta means final minus initial, so this is K final minus K initial, plus UG final minus UG initial, plus delta E thermal equals 0. And again, for thermal energy, we do not put a final and initial value because we haven't learned how to calculate an absolute value for thermal energy. We'll only be talking about changes in thermal energy. Whereas for kinetic and gravitational potential energy, we actually know how to calculate specific values for them. So we know that the kinetic energy is 1/2 mv squared, so his final kinetic energy is 1/2 m vf squared. His initial kinetic energy is 1/2 m vi squared, and that's 0 because he's starting from rest at the top. The gravitational potential energy, the final is mg times his final y position, and we might as well define the final y position to be 0, and the initial y position then is 4.2 meters. It only matters that the difference of these two values is 4.2 meters. It doesn't matter which one we say 0. If we had made initial value 0, the final value would have been minus 4.2. We'd be 4.2 meters below. But it's sort of natural to make the floor be 0, and that means his final gravitational potential energy is 0. His initial gravitational potential energy is then m times g times 4.2. So this equation then becomes K final, which is 1/2 m times 2.2 squared, minus 0, that's Ki, plus 0, that's UGF, minus UGI, mg times 4.2, plus delta E thermal equals 0. And we're asked for the change in the thermal energy, so we just rearrange that equation. Delta E thermal then equals mg times 4.2, that's his total initial energy available, minus 1/2 m times 2.2 squared. That's how much of that initial energy went into kinetic energy. And we get then m, which is 80, times g times 4.2 minus 1/2 times 2.2 squared. And that gives us delta E thermal equals, to grab my calculator, about 40 minus 2 times 80. It's dominated by that initial term. Let's see, 9 times 4.2 minus and I get 2.83 times 10 to the 3 joules. Question doesn't ask for it, but we can compare that to the total initial energy, which is just mg yi, which is 80 times g times 4.2, and that equals 3.29 times 10 to the 3 joules. So in order to avoid hitting the ground very quickly, the firefighter grips the pole pretty well so that there's a lot of energy dissipated in thermal energy as he slides down. In fact, that's the whole reason for having the pole there. Otherwise, he would just jump, and that's about a 20-foot drop, so he'd be moving very quickly and maybe break some bones without getting rid of a lot of his initial available energy into thermal energy via friction with the pole.